Welcome back to the channel. Today's video is all about understanding how modern AI models are customized using different fine-tuning techniques. Before we jump into any code, it's really important to get an intuitive understanding of what's going on inside the model when we apply these methods. Because once you have a grasp of this, the code becomes much easier to follow. In this video, I'm going to break down the three major fine-tuning approaches: full fine-tuning, PEFT, and LoRA. These names are thrown around everywhere, in tutorials, GitHub repositories, even in research papers, but most people only understand them on the surface level. So I'll use a simple, colorful diagram to walk you through exactly what each method does, why people use them, and where each one makes sense in real projects. By the end of this video, you will know not just the definitions, but the real mental model behind each technique. And only after we fully understand this foundation, we will move to the code in the next video. Before comparing techniques, it's helpful to visualize what a base model looks like. In the diagram you see on screen, the vertical stack of colorful blocks represents the layers of a pre-trained transformer model. These layers contain knowledge learned from billions of sentences, logic, reasoning patterns, grammar, world facts, coding knowledge, and so on. Even though the model is extremely powerful, it often doesn't know the specific domain you care about. It might not understand the construction document, the inspection reports, the medical summaries, the engineering calculations, or whatever industry you are working in. So our goal is to adapt this huge pre-trained model to our specific tasks without losing the general capability it already has. This is where fine-tuning comes in. Let's start with the full fine-tuning, which is the leftmost column of the diagram. This is the oldest and most brute force method. When we fully fine-tune a model, we literally retrain every single layer of the network. All the colorful blocks on the left side get replaced by new blocks labeled updated layer 1, 2, and so on. This means is you are modifying the entire neural network. The model receives your new training data, your new tasks, and it resets and adjusts every weight matrix to incorporate your domain. This is extremely powerful because it gives you full control. If you are working with a huge data set, something like millions of medical articles or legal documents, full fine-tuning can transform a general purpose model into an expert level model in that particular field. But power comes with a cost. Full fine-tuning requires a massive amount of compute. You need multiple GPUs, lot of VRAMs, long training times, and even after all of that, you risk destabilizing the original model behavior. One mistake in the training process and your model become worse instead of better. Today, full fine-tuning is mainly used by large companies with specialized datasets, such as deep research labs or organizations with extremely specific tasks. Let's move to the middle section of the diagram. Here, you will notice that the pre-trained model layers stay exactly the same. They are frozen. Instead of modifying the original layers, we attach small adapter blocks to them, those blue bricks you see here. The approach is called PEFT, Parameter Efficient Fine-Tuning. PEFT is a revolutionary idea. Instead of updating billions of parameters, it only updates a tiny fraction. This approach reduces memory usage massively. Training becomes so much faster and risk of destroying the base model disappears because the base model layer stays frozen. You can even train multiple adapter modules for different tasks. For example, one adapter for legal document summarization, one for building inspection comparison, one for invoices, and then swap them in and out without retraining the entire model. This makes PEFT perfect for startups, solo developers, small companies, and anyone building real-world AI applications without billion-dollar hardware. Now, let's look at the rightmost part of the diagram, which shows LoRA. You will see the same pre-trained layers, but this time, instead of side adapters, there are tiny red blocks labeled LoRA sitting inside each layer. LoRA is a specialized type of PEFT, and it has basically become the industry standard. Instead of training large adapter modules, LoRA injects extremely small, low-rank matrices into the network. These tiny matrices capture just the changes needed to adapt the model, while original remains the same. The magic of LoRA is that you're often updating less than 1% of the model parameters. This makes LoRA incredibly lightweight, extremely cheap to train, and easy to store. And because LoRA doesn't override the original model, you can load and unload LoRA adapters instantly. Even stack multiplies adapters at once. So LoRA is like giving model a set of task-specific personalities that you can switch on and off depending upon what you need. For example, construction compliance, financial documents, legal analysis, whatever your application requires. This is why LoRA is most popular method today. It offers best balance of speed, cost, safety, and performance. Now, hopefully, you have a clear understanding of how these three techniques differ. Full fine-tuning updates everything. PEFT updates small add-on modules. LoRA update ultra-compact low-rank matrices inside the layers. In the next video, we are going to turn this into real code, and I'll show you how to load a model, how to attach LoRA adapters, how to train them, how to generate predictions with your custom-tuned model. If you haven't subscribed to my channel yet, make sure you do, because now that you understand the concepts, the code will make perfect sense. I'll see you in the next video.